Institute of Technology, Sweden. And today I present research result we have done with my colleague, Lawrence Henesey. He is assistant professor in Blekinge Institute of Technology. Our research was done during the Connect to Small Ports project 2 years ago. That was finished 2 years ago. It was last for 3 and 3.5 years due to COVID, well-known situation with the COVID, yeah. And this research project was dedicated to like south region of Baltic Sea, and five partners participated in that project from Sweden, Denmark, Germany, Poland, and Lithuania. The aim of the project was to disseminate and collect knowledge regards to small ports, digitalization, and yeah. The agenda for my presentation is on that slide. So it includes the briefly introduction to automated identification system, AIS. Then I will briefly talk about maritime traffic data and vessel surveillance technologies. I will then outline the problem, which is the plain text data in cloud-based maritime traffic surveillance systems. Then I will describe one of the solution for the confidentiality for such data that we have chosen for our study, which is attribute-based encryption, and the role of key encapsulation mechanisms in that technology. Then we will outline the proposed solution, which is end-to-end encryption system for AIS data at store. And I will briefly talk about the experiment design and the results while we retrieve during the evaluating the cryptographic migration scenario. And to summarize, I will describe our contribution and the results. Okay, automated identification system, AIS, is the technology that allows you to collect information about the movements of the vessels in the sea and oceans. Each vessel equipped with a transponder, like a small device that periodically sends a certain information about the ship characteristics to the coastal station that collect this information. On the illustration on the right side, you can see that cargo vessels send this information to the to the vessels around them in order to avoid traffic collision, for example, or to to understand the traffic situation around them. During that data exchange, each vessel sends its position, speed, course, vessel identification number, vessel name, the status, including the draft, like how much the vessel is loaded with the cargo. Also, AIS data may include destination and estimated time of arrival. And in some cases, AIS data of certain formats being used by the ports in order to understand situation about incoming vessel. So this is, it's obvious that such a data, it's very essential for vessel traffic management, collision avoidance, monitoring, and surveillance, and nowadays, of course, for the port safety and security. AIS data is essential part of marine traffic data. Collecting and processing this data is very important nowadays for logistic industry and management of various of systems. On the right picture, you can see the representation of the cargo vessel traffic in the Baltic Sea. Each arrow is the vessel and like going to a certain destination. This information helps for vessel traffic to optimize navigation and provide efficient planning for cargo discharging or charging and port operations. In port management, it helps to improve the port operations, avoid the bottlenecks, and enhance logistics, and which also allows to efficiently manage the trade efficiency. As for the security and safety, historical AIS data provides AIS not only provide real-time data for the movements of the vessel, but also can be used for historical reasons to understand the traffic and keep track audit log of all operations in the port. So the data is used itself to keep the registry of all incoming, outgoing vessels. In our study, we have choose to research a real-world scenario with a cargo traffic situation in a small corridor in the Baltic Sea, which is provided here. So it's between the Sweden and Germany. This corridor has been very extensively used, as you know, by many countries like Sweden, Finland, Russia, and then Estonia, Latvia, Lithuania, Poland, and Germany. Yeah. So you can see on the slide the example of surveillance region, and then on the right the representation of the traffic density within this period, retrieved from the data set that we have obtained from the marine traffic service provider. So let me outline the problem with plain text AIS data. Plain text means that currently all the AIS transceivers, the equipment on the vessel, sends the AIS packets in the plain text. So it's not protected, not encrypted. There is no integrity control. And this data includes the vessel identification number, like MMSI, position, coordinate, information about the course, about the voyage, vessel name, type, time of arrival, and destination. And in our data set, we have information about traffic within the period for about 1 year, a little bit more. And there was a little more than 1 million of records. And about per hour, let's say it was about 100 of events. So it is visible on the table on the right. So within the resolution of 10 minutes, yeah, the service provider provided us this data set with this resolution. Yeah, and the traffic area covers 2,000 square kilometers. According to International Maritime Organization, the which provides the specification of AIS technology, the publication of AIS data in the web or in the open sources on the web is maybe sensitive that relates to the safety and security of the ship and port facilities. So the organization recommends to keep this information like with the certain access control. So, but as we see on the web, historically, this data is sometimes publicly available, and sometimes available from the commercial providers for a small fee, because many agencies have a need for this data, and they use it for enhance the operations and management for the transportation, like players from transportation industry, logistics operators, ports, like local port government institutions. Just a second. So yeah, it's feasible to research on the confidentiality technologies for this data, and as we later see, the confidentiality is can be reviewed as the confidentiality in transit and in yeah, and at rest. So if the data is within the communication channel or it's in the data storage. As for related research, we have identified that mostly existing research covers the encryption in transit, so confidentiality for the AIS data, which is in the communication channels. Means the between the AIS transponder to the AIS receiver station. But it doesn't cover the data at rest. It means when the AIS data is retrieved in plain form, that it's usually being stored in the plain text as it is, and it's obvious with the satellite AIS. This technology allows to capture AIS data packets over the air. It means on the low orbit satellites, capture this data almost in real time, and then provide the various services for surveillance or vessel traffic information in real time. So mostly the problem is very important, and existing research trying to tackle the problem with well-known technologies such as public key encryption, public key infrastructure, and also one of the latest paper covers identity-based encryption. This is to eliminate the cost of certificates in public key encryption infrastructure. And so to avoid the issuing the certificates and having certificates of authority, the identity-based encryption allows to use certain certain central authority that allows to identify each participant by using a normal string, such as like ID number or email, for example. Also, it's good to mention the Tesla authentication protocol that work to mainly contribute to the integrity and authentication of AIS data, like vessel to vessel or vessel to coastal station. Also, exist commercial products that that produce the AIS equipment with the built-in encrypted communication capacity. So you can have your own fleet with equipped such products that will exchange the information in encrypted form. So your fleet will be able to use the AIS technology in highly confidential form. The solution that we proposed in our study relates to public key encryption, but we tried to cover the situation with the encryption for data at rest. So to protect the confidentiality for historical AIS data, which is stored in the cloud and provided to the end users. So just to remind you about the public key encryption, if we have a plain text, so we're using a public key and we can encrypt ciphertext by single private key, and then entire let's say document or a data is being encrypted and can be decrypted by the holder of private key or secret key. The alternative, which is number 2, attribute-based encryption, provides a bit expansion of this limitation, the solution of this limitation. So to encrypt the document or the data block with a special access structure, so then ciphertext will be encrypted in such a way so a group of people with the special secret keys can decrypt only a portion of this text. So on the illustration, you can see that now ciphertext has a more composite structure. So the colors within the document highlights the on this example the exact structure for the 4 parties, for recipients, and central authority controls which recipients or which members will be able to decrypt the ciphertext, which is very useful. This concept appeared in 2006 by the Goel in the paper about attribute-based encryption and fine-grained access control. We drive our research toward this technology. And just a second. Oh, okay, that's next slide. So in our proposal, attribute-based encryption can be used for the historical AIS data and certain fields, certain type of the fields in historical AIS data can be used as the access criteria when we will encrypt the data with attribute-based encryption. So, for example, we can use a vessel ID, like MMSI code. We can use date and vessel type, coordinate as the criteria for access for the to decrypt, to access and actually decrypt historical AIS data. So on a given example, decryption will be successful only if the recipient has a special secret key that complies with the given access structure provided, and this access structure can be designed by authority or AIS data transporter, but the secret key created at any time by the central authority. Our next part of the solution is end-to-end encryption approach for AIS data, which means that exists a certain confidentiality perimeter, which and it is highlighted as green on the illustration on the left side. And within this perimeter, the data is only within this perimeter, the data is in plain form, like accessible for the participants. So in this example, the data originates in the AIS equipment or satellite AIS system, and that like data source 1 or 2, and then by using the end-to-end encryption approach, it encrypts for a certain user, but the cloud and owner and system owner doesn't have access to the data, so they cannot decrypt it. If this technology will be presented more technically on the right side, so we can see that a special technology, which is called application layer encryption, needs to be employed on the system between AIS devices and the customer of the system or user A, and only between them exists a certain encryption decryption capacity that allows them to access plain text data. So even the data storage also have the always store the data in encrypted format, which is highlighted. So on top of all existing confidentiality technologies, which is, for example, TLS or full disk encryption for data storage, the application layer encryption adds additional encrypted layer that allows you to store information always in encrypted form. We have reviewed the real-world implementation of attribute-based encryption, studies, and identified 6 studies in different industries. And we reviewed them by certain criteria, such as computational performance, communication cost, threat availability of the detailed threat model, or description of security properties, and detailed access model. Key distribution, schema in detailed data flow, also important in the case where you need to exactly specify the roles of the members within the system and how they're going to access and distribute the keys. It's good to mention that 6 years ago, this technology were already standardized by Telecommunication Standard Institute, and they published 2 specifications. So it's a real-world technology feasible to study. And the number of studies grown within the years, which is demonstrated on that slide also. So we continue our study to research the cryptographic library, open source, available on the web, and we review them by a certain criteria and identified that only a few libraries use so-called encapsulation functionality, which is actually implements encryption system in hybrid mode. So they use public key and encryption principle to encrypt a session key and then use the conventional cryptographic primitive, such as AIS, to encrypt arbitrary data of any length. So according to this review, we have choose OpenABE library that based on the Relic mathematical library. Then we have designed our experiments and we identified that key encapsulation mechanisms, it's a new direction in cryptography, and in fact this is the also public key encryption, but it's this concept separated from public encryption because of a natural development due to efficiency and to modularity in hybrid encryption technology. So the KIM mechanism specifically responsible for encrypting this small session key, but the other components responsible for the encryption for the regular data. Also, recently, NIST published the next standard for the KIM, and CRYSTALS-Kyber won the competition, and NIST, National Institute of Standardization in USA, they promote the development of key encapsulation mechanisms because of a certain capacity, such as in key encapsulation mechanisms, the session key has been generated by the underlying library, but not provided by the sender. And so our proposal was to simulate cryptographic migration to multi-party key encapsulation mechanism. So we experimented with the CRYSTALS-Kyber and OpenABE, compare them by certain metrics. The results, we obtained the results. So after comparison and running our experiments for on the CPU on 3 performance rating. So on this picture you can see the highest performance rating, and where it's very obviously that Kyber is very efficient in terms of computational cost, but it's not so efficient. It's not so efficient like 10 times less efficient than attribute-based encryption, but this is like due to a special like mathematical structure, and it takes more space like to represent the objects from the like lattice math, and because of the highest like security level that we have experimented with. Both libraries allows you to like run operation in stateful model. It means the encapsulated key can be used across multiple encryption operations for the arbitrary data. And it is up to like cryptographic library consumer to decide how long to use the session key. But the Kyber is resistant to many like attacks, like that was I highlighted this here in this slide, like against adaptive attacks such as chosen ciphertext attack. Yeah. I think I'm done, and just a few words about future research. It's about the cryptographic API metadata and abstraction layers. It relates to cryptographic library use. We also focus on real-world scenario for threat model and multiple recipients key encapsulation methods. We also plan to evaluate key encapsulation mechanisms in high assurance cryptographic library, and experiment with that. And I will continue to work under my cryptographic agility manifesto, which I recently published, and also I will present it in the next conference in November. Thank you. I think I'm done.